Modern warships are floating cities of integrated electronics. But if a single fault rips through the right electrical node, thousands of tons of advanced engineering will instantly go dark, leaving the crew paralyzed in the middle of a hostile ocean. This tension between theoretical design and battlefield reality has haunted the military for decades. During World War II, the Bureau of Ordnance deployed the Mark 14 torpedo. It cost $10,000 per unit, the price of 5 family homes at the time, and was touted by its creators as a flawless mechanical predator. Today, that same ambition scales up to the Arleigh Burke-class guided missile destroyer. Ships like this represent the apex of modern naval engineering, packed with intricate radar towers, integrated power systems, and automated defense networks. Yet both the World War II torpedo and the modern destroyer share a dangerous lineage. Their highly complex systems are born, calibrated, and perfected in strictly controlled, isolated laboratory environments. When engineers prioritize pristine, sterile test conditions over the unpredictable swells of the open sea, the sheer complexity of the machine can become a greater threat to a crew than the enemy they are fighting. To understand why these advanced platforms are vulnerable, we have to look at how their software is built. Combat systems like the Aegis network are designed as proprietary stovepiped suites. They are custom-built exclusively for specific ship classes, tightly binding the code to the hardware. Because developers build these systems in isolated silos, they reject an open architecture approach. A sensor or control module designed for a destroyer cannot be easily shared, upgraded, or adapted for a frigate or an aircraft carrier. At the core of these platforms is the Hatley-Peerby modeling framework, which governs 3 primary functions: detecting, controlling, and engaging threats. The danger lies in how rigid this framework is. Because these functions are locked inside a closed-loop, non-reusable software architecture, introducing just one unforeseen variable from the real world can disrupt the entire sequence. Designing bespoke, inflexible systems transforms a warship's advanced integration into a massive liability. The moment the environment deviates from the parameters tested in the simulation, the entire platform risks breaking down. We can see exactly how simulations fail by looking back at the laboratories of the 1930s. Peacetime testing protocols completely masked fatal physical flaws in the Mark 14 torpedo. Engineers calibrated depth controls using hollow, water-filled exercise heads, but in combat, the weapons carried a massive, explosive-filled Torpex warhead. The extra weight in the nose forced the torpedo to dive, running 11 feet too deep and passing harmlessly beneath target keels. The torpedo also featured a top-secret magnetic exploder, designed to detonate when it sensed the field of a steel hull. However, the engineers calibrated its sensitivity exclusively for the high magnetic latitudes of their testing facility in Rhode Island. When submarines fired these weapons in the equatorial waters of the Pacific, the Earth's magnetic variation was entirely different. The hypersensitive exploders would trigger prematurely upon hitting the friction and turbulence of storm-driven waves. Optimizing a weapon's sensors for a peaceful, protected New England harbor guarantees failure when the machine is finally exposed to the chaotic variables of an open war zone. That exact same over-reliance on theoretical modeling is now built into the power grids of today's billion-dollar destroyers. It manifests in the integrated power system. This diagram details the new integrated electric drive. Instead of separate engines for propulsion and operations, a single set produces a common pool of electricity, feeding both the propellers and the ship's internal loads. Turning the propeller relies on a permanent magnet motor. This introduces a severe electrical vulnerability. If an internal fault, like a short circuit in the stationary coils, known as the stator windings, occurs, the crew cannot manually turn off the magnetic field. Permanent magnets, by definition, are always active. As the ship moves forward through the water, the passing current spins the propeller. That spinning motion forces the motor to act as a generator, taking kinetic energy from the ocean and feeding electrical power backward directly into the short circuit. By tying all critical functions into a single, highly sensitive power grid, engineers created a fragile domino effect. One localized fault in a motor can instantly disable the propulsion and drain the electrical lifeblood from an entire warship. For the submariners fighting in World War II, the failure of these complex systems reached its breaking point in June 1943. The USS Tenosa cornered a stationary Japanese tanker and fired 15 textbook shots. Every single torpedo hit the target with a hollow thud and sank to the bottom. To find out why, the Navy's engineering chief, Swede Mommsen, bypassed the laboratory simulations entirely. He took a warhead to a Pearl Harbor cliffside and dropped it onto a steel plate to test the raw deceleration physics of a combat speed impact. He discovered that the extreme impact forces of a perfect 90-degree hit were physically deforming the firing pin's guide blocks. The immense pressure clamped down on the pin, jamming the mechanism milliseconds before it could strike the primer. Because the isolated developers refused to test real-world impact forces, the Navy deployed a weapon that physically penalized perfect marksmanship. A sloppy, glancing blow would detonate, but a flawless, high-speed strike guaranteed a dud. We saw the modern consequences of untested fragility in May 2026. The USS Higgins, an Arleigh Burke-class destroyer deployed in the Indo-Pacific, suffered what the Navy classified as an engineering casualty. A limited electrical malfunction inside a single piece of equipment sparked and smoked. Because the ship utilizes a highly integrated system, cutting power to stop the failure cascaded into a total blackout, instantly knocking out the vessel's propulsion and entire power grid. 300 sailors were left completely stranded at sea. Without the ability to maneuver the hull or control their automated defense networks, the crew sat as sitting ducks for several hours while technicians raced to restore power. To prevent these systemic lockups, the future fleet has to abandon proprietary silos in favor of product line engineering. This chart shows how the military can establish scalable, open architecture components designed to be modular, robust, and adaptable across multiple ship classes, rather than isolated to one specific hull. Money and theory can build an infinitely complex machine, but the most sophisticated weapon is useless if it requires a controlled laboratory to survive. Only the brutal, unpredictable reality of combat proves if it actually works.